today I want to tell you about 3 situations that you might face when programming. Let's have a look at them. So the first one is when you have like a big data model and you want to serialize it to disk, but then you want to evolve your data model. How do you do with keeping up with the different serialization formats? The second situation is when you have another like big data model, and now you want to generate data out of this in different configurations for different tests with different conditions. How do you deal with this? And the third situation, which looks kind of different, is when you have a large application that needs to evolve, get more components, where you need to mock stuff out for testing or have different configurations. How do you deal with this? So it could be this application, or maybe some people in the room will know better that application. So in those 3 situations, they actually share some stuff in common. In particular, all the elements that you saw previously, they form a graph. This graph, in general, is not cyclic. Then each node in the graph has a given type. And for those 3 situations, as we are going to see, it is going to be very, very useful to be able to take that graph of entities and just being able to replace some of them without having to rewrite the whole graph. That's the whole point. Because if our code is large, we don't want to rewrite everything all the time just to modify one small thing. So it looks a bit abstract. Let's dive into some examples and have a look at encoders and decoders. So let's say you are writing with some kind of blockchain, but it could be an immutable ledger, where you have this idea of putting some kind of transactions or events to a log that's immutable, where each event describes some kind of action acting on some state. And that's, this kind of the functional programming that we truly love, because then you fold on those events, and then you arrive at a new state, and if someone else does the same thing and everything is deterministic, we should arrive at the same state. So this has all sorts of very nice properties. The trouble is that your application is also going to evolve. So everything that you have put in your log, you still need to be able to read it again and then have new versions put on the log, and you need to keep up with all those versions, right? Let's have a look at an example of what this could look like. So let's say if on my ledger, immutable ledger, I'm putting something like a transaction, and it's a large data model, so it has things like, okay, who signed the transaction, what's the metadata, and each transaction describes a command for a given protocol, for example, where you can create, I don't know, communication channels and stuff like that. And if you're working in a blockchain domain, maybe you have some smart contracts that you want to execute, so you need to describe all of this. What does it mean to execute a smart contract? You need to say which contract, which function, which parameters you're going to use. So all of this, at some stage, needs to be serialized somewhere. So how do we generally deal with the situation of serializing stuff on disk? So that doesn't display really well, okay. In Haskell, one of the things that we're using is generics and type class derivation. And okay, opinion number 1 here, there are going to be a few opinions in that talk. Generics might not be the best idea. And at first, it looks like a great idea, because you define your data type in Haskell, and with just 2 lines, like deriving generics and deriving to JSON, you have an encoder for that data type. And that thing can be quite complex. And all the code for that encoder will be just generated for you automatically, which is fantastic. But the trouble is, how do you evolve these data models? So let's say, for example, that in our previous example, you have parameters for those smart contracts, and then you realize, oh, each parameter can be quite large. The rest of the commands on disk, they take almost the same size. But one thing that varies a lot is what users are inputting as parameters. So it's like a big blob of JSON. And you're thinking, oh, I'm not even interpreting this piece of JSON in my system, so it's just data in transit. So I could just compress it. I wouldn't see the difference. So now the question is, how can you keep up with having on your ledger both compressed data and uncompressed data that you still need to be able to read and interpret? And in general, when you talk to people about type class derivation and like the advantages of type class and deriving instances like to JSON and from JSON, and you say, oh, what if I need a different behavior? And people tell you, well, just use a new type. It's kind of obvious. You want a new behavior attached to your data type, then you need a new type. The trouble is with this approach is that if this type is used in a graph of many other types that depend on it, then that new type, something else has to depend on it. Like, so the compressed parameters new type needs to be depended on by something that you have to call compress contract something, and this thing is kind of viral. So if you start by modifying something like at the bottom of your graph, it spreads to the almost the rest of the whole of the data model, maybe 80% in some cases. So in that case, generics and new types, they don't really help us to solve this problem of how can you evolve your data model in corresponding to your serialization instances, because the two are very much coupled. So what do you do? Before we saw what to do, I want to show you why generics can be also a pretty bad idea. And this is like a real-life example. So at work, we're using a library for serializing data as message pack, which is a binary format for JSON. And then the thing is, no one really looked at what was really serialized on disk. What did it look like? And then we wanted to think, oh, let's try to specify how the data format really is, because maybe someone else wants to also read it, maybe using another language. And then we had a look, and it looks like if you have a data type with just 2 fields, well, the 2 fields, they go in an object array, and it's fine. Then you add the third field, it goes in the array. And then you add another field, 4th field, all of a sudden you start getting nested arrays. I mean, that still serializes, but it's not so nice. You would expect like 4 fields in an array, not a nested array. And how are you going to explain this to someone else who doesn't know anything about generics, GHC? Because it turns out that this is really related to how generics are encoded inside GHC. And the people making that library, they said, oh, let's like do a one-to-one mapping and just serialize this, and this would work. So maybe using generics blindly is also not such a great idea. So what can we do? Well, some people, they say, well, just bite the bullet. I want a data model, and if I need to export it to version 1, version 2, have different interfaces to that data model, well, I need to bite the bullet and create as many other models that I need to do the job. And for people who've been using Java for some time, maybe you remember this as data transfer objects, right? The advice was like, okay, you have your object model, which is really nice, containing all the business logic. And then if you need to persist anything or serialize anything, just create a brand new model. The trouble is that this approach, this does not really scale, because then it's hard to maintain to have so many models with just one thing to do. So maybe not the best thing to do. So let's try to see, what if we were to do all of this manually? Like, what if we had to write this code and not having been generated from us? Can we start from there? So let's say you need to describe an encoder as any function that takes an A and returns a JSON value, for example. What do you need to encode the whole transaction? Well, you need encoders for things like ints, for strings, for byte strings, like low-level types. And then based on that, you can create other encoders, taking those encoders as parameters to build an encoder for a contract, then build an encoder for a command, and then build an encoder for a transaction, right? So you build progressively the encoders you need by creating functions, taking other encoders as parameters. That's what you would do. And eventually, you arrive at this big expression representing an encoder for a whole transaction, for the whole of your data model. So what happens then if you need to evolve your data model? Well, you have an expression, so you can parameterize it. You can say now, oh, actually, my encoder for parameters needs to be slightly different. What do? I make it an argument to this function, and then I pass it everywhere it's actually needed. And if I need version 1, I'm passing the encoder for version 1. If I need version 2, I'm passing the encoder for version 2. So this works, but this is pretty ad hoc. So what happens then if you have other evolutions in your data model? And this is still lots of boilerplate. And it's kind of a shame, because most of this expression is pretty mechanical. If I give you all of those functions and I tell you, produce me an encoder for a transaction, it's like a puzzle. You say, oh, I need to, and for an encoder for a transaction, I need an encoder for a signer, I need an encoder for metadata, and so on. So based on the types, you can actually reconstruct this expression, because this is just doing function application driven by types to build this expression. So why not have some piece of code do that for us? And that's the idea of this library called registry, where you put functions to build other things in a list. And then you have a simple algorithm with the make function here that is going to go through the list and say, okay, you want an encoder for a transaction. Is there a function returning an encoder for a transaction? And you go from the top of the list to the bottom. If you find one, in that case, that's the first function, it makes an encoder for a transaction. Oh, but it needs some inputs, other encoders. And you go recursively like this. You go through the list for every input you need until eventually you have all the inputs you need to build everything, and you do function application of all of this until you can build your overall encoder for a transaction. That's as easy as it is. The thing that you do additionally is that every time you make something, you put it on top of the list so that you don't have to make the same instance of the same type twice, right? Otherwise, it will be expensive to do so. But not only it's a good idea to do it for performance reasons, but as we're going to see, it's also a good idea in terms of features for this library. You might object that all those functions, you still have to code them by hand, and all of them are still fairly mechanical. So you can still use something like template Haskell to produce those functions for you. And in one of the libraries I've been using, you take a constructor for any data type, and you can have a piece of template Haskell that is just going to produce this function. But because everything is in a list, that gives us some additional power. And what is this power? The power is that now, if you want to describe a different way of serializing stuff that is just slightly different from the previous one, you can say declaratively, you can just say it. You can say now, my new encoders are exactly the previous ones, but for parameters, you just use this different encoder and you put it on top. So now you describe version v2 as v1 plus something. And because of the algorithm and the way it works, it will, if you're using version v2, it's going to take the new encoder everywhere it is needed. So now we described with one small modification, like incrementally, just the change we wanted to have, to see. Okay, let's have a look at another example which looks different, but it's actually fairly similar. Let's have a look at data generation. So how can we generate data in Haskell for writing some tests? So you have in Haskell two libraries, there's actually three now, where you can generate data and run some tests on arbitrary data, so quick check and hedgehog, for example. How do you do the job using these libraries? So let's have a look at quick check. And again, I'm going to say type classes might not be the best idea for data generation and driving data generation. But at first, it looks like a great thing. And I mean, when I discovered it, I found it very nice. For example, the fact that you can take a data constructor like contract and use the applicative notation and say now all the rest is arbitrary generated data is great because you don't have to say which type you want. It's automatically inferred. So in terms of maintenance, that is great. If you change the type of your field, this expression doesn't change. So that's cool. It starts being a bit less cool when you have to add a new field because then you have to come back to this expression and say, oh, I have a new field. It looks like a fairly mechanical change. And again, you just wish that the software somehow would understand this and add this new field for you. But it doesn't do it. But the worst thing with type classes and data generation is not this. It's the fact that using type classes in Haskell, we are striving to have just one instance for one type class and one type, right? And we should not break that rule. It's an important one. So, but it's not applicable to data generation. When you generate data, you want to generate all sorts of different data for a given data model where you say, give me transactions with no send key. I want to fix the contract version to be 2. I want to generate 2 transactions and make sure the signers are different on those transactions and so on. So this is actually one reason why the people who did the hedgehog library for Haskell, they just got rid of type classes. They said, they don't help us in that case. Let's just provide, create, or run data generators, have a bunch of combinators, and combine them together. But then you are left with this huge expression of things being wired together that you still have to maintain manually. So let's have a look at an example of what you can do using the same approach of using this registry approach to building things. And for this data model, we're going to make it slightly more complex and add a field that is a maybe of a text, and maybe have a list of parameters instead of just one. And now you can have actually the exact same approach. So you want to generate data for a contract or transaction. The contract constructor or the transaction constructor, they are functions, right? They are functions taking parameters, returning something. So you can lift those functions to a function taking a generator, another generator, and returning a generator. Like, so you want a generator of person, you take the person constructor, you need a generator for the name, generator for the age, now you have a generator for the person. So you can take all the constructors of your data model, you stick them in a list of functions like this, and then you say, give me a generator for transaction, and it's going to build all those generators for you. You even have, actually, to specify relationships between entities. Like, if you have a maybe of something, you need to say exactly how do you want to generate this. And in some cases, you might want to say, generate 50% of the time, you generate some or none, or maybe you want less nonce because it might not make sense to generate nonce one times out of two. You still need a bit of template Haskell because there is still some boilerplate. And actually, there is even a full Haskell library dedicated to just solving that use case, which is how do you generate data for an ADT? Because each constructor in an ADT takes different parameters, possibly, and returns the exact same type. And given the algorithm I've described, every time you find a function that returns you that type, you use it. So if you would apply the same strategy like naively, you would just always use the same constructor, which is not what we want. So it is actually possible to work around this limitation by tagging each type with a new type, and then having a combinator that's going to combine which constructor you want based on some kind of frequency, for example. And again, yeah, template Haskell can help you just write that code automatically for you. But now that you have this, if you have the list of all those functions using generators, you have some superpowers that are really great. Because if you want to say, in my big data model, I want now to generate commands that have no send key operation. Never. I'm not interested in that for my test case. What can you do? The one thing you can do with the library is use a function called tweak. And what tweak does is that every time you build something, when you place it at top of the registry so that it's always used again, it allows you to apply a function to it to modify it. So you can modify something just before it is stored. That means that in that case, we can use this tweak function to say, oh, every time you build a command, just filter it before. So make sure that there's no send key operation. And if during the generation you find a send key, you just discard that value, try to generate the next thing. So the cool thing about tweaking something is that you can take an existing registry, list of functions describing all your generators, and just modify it to have a slightly different behavior in just one place of the generation. And if you use this in an actual test, and if you collect all the values, you will see that there's no send key operation being generated in that example. And actually, you can go even further. In some cases, it's even useful to be able to say, oh, actually, I want my contract version to be only 2. And you could say, oh, what if I just place a generator on top of all of this, saying, now, every time you generate an int, you set it to 2. Well, that would be a bit naive, because you don't want 2 to be everywhere. So one thing you can do also with the library is you can specialize one of the paths, where you say, now, when you build my graph of things, depending on each other, when you are generating a contract, actually a generator for a contract, now make sure that the generator for ints is set to 2 all the time. So it's like you make a contextual change in your whole graph. And I think that's pretty powerful. The other reason why it's pretty powerful is that what I described before, tweak and specialize, they are both operations from registry to registry. It takes a graph description, returns a graph description, which means that you can compose them. So you can have arbitrarily complex ways of modifying your generation strategies and compose them to get other generation strategies by just describing the parts that you need to change in between. And another thing I need to say is that at first I said we don't deal with acyclic graphs, but actually you can still do this. And for data generation, there's at least one case where it's really important to be able to do so, is for JSON values. So there's an extension of the library that can generate JSON values. But you need to do it pretty carefully because you need to make sure that you distinguish the recursive case from the non-recursive case and know when to stop. But it is still possible to do so. If you're interested, you can have a look at the library to see how to do this. Let's see another example. So now we've seen encoding and decoding, like large number of encoders, decoders depending on each other, then large numbers of generators depending on each other. And again, I'm saying large because those things really matter at large. They matter when maintaining code is really something that is burdensome, when you don't want every time you modify one line of code to have so many repercussions around that are silly repercussions that you have to modify just to try something out, for example. So actually, the library was born out of a desire to solve this problem. How do you build large applications in Haskell for people that are not necessarily very familiar with Haskell or the type system in Haskell? And let's have a look. So such an application, if it's large, it has generally like several layers. It has like low-level components, middle-level components, high-level components, and complex relationships. And some components, they are actually used everywhere, like logging or tracing. We can find dependencies on those components almost everywhere. So, type classes. Is it a good idea? No, it's not a good idea. But let's see why. Because at first, type classes, they look like a great idea, right? A type class describes an interface with all the operations that something should do. And then you have an instance describing the implementation. And then it's kind of the holy grail of modularity, right? And building systems. You have a clean separation between an interface and implementation, and then you can vary the implementation without impacting the clients of the interface. That's exactly what we want to grow systems. And for the instance, you can describe the dependencies. So you can see again this kind of graph that is purely described and specified here. And then all the wiring happens magically because GHC does that for you. It takes all those specifications, builds the instances, and wire them for you so that everything is wired together. But the problem is that, again, type classes, you're not supposed to have so many instances per type class. And for building applications, that's really a problem because how do you test applications? How do you switch one component with another just to have some mocking? Maybe you don't want to talk to your database all the time to test one simple thing. So that is annoying. So what are people recommending in that case? So some people will tell you, well, you can use an effect library. And I also think that's a bad idea. That does not solve the problem. So there are many different issues, I think, with effect libraries. So maybe the first one is like the approach to using an effect library to build applications is this idea that you can build small languages and build expressions that are going to be interpreted progressively, like reduced to simple values using different interpreters that can be composed together, which, I mean, that looks great. But the first thing that you have to introduce is a separation, you have to introduce your language. You cannot use functions directly anymore. You have to use data types that are representing your functions. And at large, that makes the code a bit hard to navigate. That is one issue. The other issue is that for those libraries to be useful in any kind of production scenario, they have to be higher order. So there are many effects that takes other effects as parameters, like concurrency, resources management, even a local reader. And the cool thing is that they support this. And it was not always the case. I mean, I've worked with a library that was not supporting this, and it was a real problem. But now we have libraries that support this. That's great. But this comes at a price. This comes at a price. There's a cognitive load associated to this. Now you have to understand a lot more concepts in order to be able to use the library, to build the interpreters, and so on and so forth, which is kind of annoying, again, if you have people that are not so familiar with this. But I would say maybe the worst is that this does not solve the problem. Because at the end of the day, if you have one effect per component in your architecture, and you have at least one interpreter per component in your architecture, you need to interpret whole expressions by stacking those interpreters and saying which are the interpreters that are going to interpret everything. And this piece of code where you stack everything up, it's like the same expression we had at the beginning. It's a big monolithic expression that you cannot parameterize right away. If you want to change one interpreter in the middle. You can copy and paste the whole expression and just change the line in the middle, but that's copy and paste, which means that's a future maintenance burden. Or you can start introducing parameters to parameterize this expression with being able to replace one interpreter, and then good luck, because the types might be actually quite involved in describing this transformation. So maybe not such a great idea. And the third idea is to use a variation of reader T, which I think actually is something that works. But it only works on small-ish applications. Because with the reader T thing, you can put some components in your environment and then use them everywhere you need them. But it only works at one level. You can only put in your environment low-level components that higher-level components are going to use. You cannot put the higher-level components themselves in the environment. So you're limited to smaller applications. So let's have a look at, okay, what if we were doing this manually? We can define interfaces in Haskell by just putting functions in a data type. So you have a record of functions, and that defines precisely an interface. We can have a function that builds values for this data type, taking other interfaces as parameters, and then you can implement each function and provide it to the rest of the world. So here we build a value store, for example. And the syntax is actually quite nice in Haskell to do this, and if you squint a bit, it almost looks like, I don't know, an object-oriented class, right? That closes over all the parameters that are needed to do the implementation. But still, if you go through this approach, which is sometimes called the handle pattern in Haskell, you still have to do all the wiring manually. And it can be even quite tedious, because when you create components for an application, the creation itself is effectful in general, because you need to, for example, create connection pools, which is not a pure operation, and there are a bunch of initializations that need to happen. So this is some code that can be, again, a bit difficult to maintain. So we can apply the same strategies. We have now constructor functions to construct those components. We can put them in a registry and call the make method and say, make me an app. And it's going to call all the constructors, find the low-level components, and progressively wire everything up until you got your application. That's really cool. And you have lots of profits out of this. And one of them, which I really love, is that if you want to change the implementation of one component and you need a new dependency, well, you can just add your new dependency to your function here, and none of the rest of the code anywhere has to change. Because in your registry list of functions, nowhere you are mentioning the exact list of parameters that you are using or the number of parameters. You don't declare this, you just give the function name. That's all you have to give. So one local change. So it's nice for experimentation, it's nice for development, it makes you faster. And then you can use the whole thing, for example, to mock some components. So if you want to mock a component, just put a different implementation on top of the list, and everywhere that implementation will be needed, well, it will be taken and be used by the other components that need it. You can, as I showed you with the specialize function, you can even say, mock a component, but only for this part, this subset of my application graph, and not everywhere. I just want to test what happens if my HTTP communication goes bad when I'm sending events, but not in the other cases. You can also describe just this transformation. And because adding something to a registry is just an operation from registry to registry, this means that you can describe all those operations as separate pieces of behavior that you can compose together. So for example, one thing you can do is have different configurations for your whole production application, where you can say, okay, if I'm deploying that thing in production, take all the components, that's fine. But if I'm using some local development, I don't want to be too far from production, but I don't need to do any tracing, for example, or any logging. Or I want to use my local database. I don't need to go to the cloud. And you can just specify this as a bunch of functions that are composed together, describing how you want things to be slightly wired differently. And another benefit that you can get from this approach is that you can also display graphs. So you can also show your data model and show your application just by walking through the registry, looking at all the dependencies, and just displaying them in the dot graph. So that's also a nice way to document your application or your data model. So I think that looks good. It looks really nice, but I don't want to oversell something. I want you to be clear about it's not like the end solution. There are still many things to improve in that situation. So one of them is that adding something to the registry can be type checked. So you can get compilation errors whenever you add a function to the registry and you have no other function producing any input for that function. And you can get a nice compilation error telling you, oh, you want to build a value store. It's cool, but there's nothing building a tracer at the moment. So I will never be able to build a value store for you. That's a nice error. The trouble is, GHC will go at big pain to show you the full expression that's wrong, which is the full registry. And that thing can be really large. So that can make pretty scary errors. And it can get worse. So everything that you put in the registry has to be fully typed. You cannot put polymorphic functions in it, and there's a reason. That's because of the implementation. It's actually a good thing for the case of generators, because it forces you to say that the generation for a maybe of text is going to be different from the generation of a maybe of int. But if you put a polymorphic function, you will get a troubling error that is maybe not so understandable, and again, with many types up in your face that you might not understand. And the worst case is we have this nice, DSL to add functions inside the registry, which is kind of cool because with this less than column, you can put two registries together. You can put a registry on top of a function on top of the registry is very flexible. You don't even have to think about it. But this DSL, in order to be implemented properly, needs to have the right keywords at the right place. If you miss one of them, you get a horrible error that, again, might be hard to understand. Another thing which I would love to see improved with GHC and Haskell in particular is that all this type checking is done with type level sets. And they are super slow. So if you want to check for inclusion of a type in a type level set, or even a list of types in a type level set, this is really, really slow. So if you have a large list, and I've been building like hundreds, maybe more than 100 elements, it can be really slow. So that's something that can be improved. That being said, if you hit that limitation, you can also use the library in an untyped way, and then you will get errors at runtime telling you, no, you cannot build something. And finally, the last point is that you still need some form of effect. That does not solve everything. And in particular, in any production application, you might need to be able to thread through some kind of context. For example, a request ID. So if you want to be able to trace user requests, that cannot be implemented by one single component. This is a piece of information that is going to throw through all the components, and at the end of the day, each component is, in general, parameterized by a monad, and what makes them work well together is the fact that when we wire everything up, we use the same monad. So all the components, they communicate using the same monad. And in that case, you will need some form of request IO, a reader T giving you access to the current request ID, for example. So I think I'm good on time. So I have time for questions. Thank you.
Thank you. We actually have a lot of time for questions, so feel free to ask them.
Hi, Eric. Thank you very much for this talk. Very interesting. So I'm personally involved with the competition because, with especially the effectful effect system. So, and you mentioned doing a registry for large applications and things that scale. So I've got some personal questions about your experience with them. Especially, I use Effectful because as an architect, for example, it allows me to see at a glance that functions interact with other parts of my system. PostgreSQL, Redis, the tracing, the logging. Is this something that you lose with registry? I only had a glance of the type signatures, but it looks to me like registry is fairly opaque. So is it something that you personally found to be a disadvantage because registry seems a little bit more opaque, and when you refactor, you have more trouble, perhaps, or perhaps not. Thinking about the interactions of your system with the other components of your architecture.
I think it's a profound question.
I know,
really.
right?
And there's a tension here between abstraction and modularity, and some kind of verification and transparency. Because when I give you an interface to something, you actually, if you want to keep your system like evolvable and like have things being nicely independent, you don't want to know how I am implemented. You don't want to know that I'm using Postgres or Redis in the background. So you don't want even to pass me this information, like use this backend for your implementation. And that decoupling is nice. At the same time, you don't know if I'm pressing the button to launch the nukes. You don't know this. So there's this inherent tension. And I think I kind of chose one camp, which is you don't have to know, and that helps the system evolve without having too many impacts. But at the same time, when you build an application, there are really two phases. There's the phase where you wire the whole application, and you could even like run tests on this wiring to make sure it's done properly. And then when you use it, and you separate things very clearly. Whereas in other approaches, sometimes with effects, it's the separation is not always so clear. Sometimes in the middle of the code, you start interpreting some stuff, and then at the end of the code, you start interpreting all the rest. And one thing which I like and which I think helps in terms of controlling the complexity is this approach where at the beginning, you build everything you need, and then you use it. And in my experience, that was beneficial, this kind of strong separation between the two.
Any more questions?
All right, I'm just a beginner at the Haskell. However, this powerfulness, what you've shown, is very appealing for me. And I wonder, what book should I read to get it, or should I read like academic papers?
Okay, so to get how it works, the basic intuition is that what I'm doing is purely function application, like putting functions and values in a list, and internally treating them as dynamic values, like untyped values. So the internal implementation treats everything as dynamic values using data.dynamic in Haskell. So you need to read about that library, how it works. So data.dynamic. Yeah. And I still keep track of all the types. I mean, what is required for each value. And then in data.dynamic, you can take a function that takes some dynamic arguments and apply them to the function. And if you didn't mess up with your implementation and the types are really the right ones, you will get a value. So that's one thing for the implementation. And then there's lots of type machinery on top in order to be able to check, for example, that a function has the right inputs, that the inputs already exist in the registry if you want to add something. There's lots of type-level machinery as well to lift a function. I said you can take a data constructor that goes from A to B to C and lift it to gen of A to gen of B to gen of C. It's not trivial. And in the case of actually components and I/O, what it does is even smarter, I would say. It goes, if it's A to B to I/O of C, it's only going to lift I/O of A to I/O of B to I/O of C, just to make sure everything is flat and not I/O of C, you see? So yeah, that is quite involved in terms of types, but the fundamental idea is just to use untyped values protected by some type level checks.
I was really excited by the when you touched on like mocking and stubbing stuff in web applications, because the code that you showed, and also I'm looking at some of the documentation that you have in the repository, it looks a lot like what we have at work. Because we have a big Yesod app. It looks very similar. Maybe this is like Servant, or maybe it's Yesod. It's a sort of web application interface type of thing. But when you read like a typical Ruby on Rails tutorial, it makes it very clear, like, here's how you write a controller method that handles HTTP requests. And here is how you can stub out the database or perhaps some network request to some other service. it makes it really concrete and easy for a developer to read that and understand it. I'm not seeing the same in the documentation here. So do you have some really concrete examples, say, of a Yesod application where it's like, here's how you stub out a database transaction?
Okay, so from time to time, I see people making repositories, comparing different approaches to building applications. So I think sometimes I'm pushing PRs to those repositories, but I haven't tracked them on my site. So I should do this. But I'm also very happy to work with you, take like a sample Yesod app and use this approach to show how it can be done.
I've got about 1,000 beers to donate to you, if you can show me that.
Yes, let's do it.
So it looks like you wrote dependency injection. Yeah, I know. Like but so I like. So what is here is like really reminds me of Juice library for Java. Like this is also like dependency injection framework or library, but it's like it doesn't contain so much magic. Yes, it's very explicit, like your approach, and it's like maybe like that. Functional people are afraid of this dependency injection term, that they have bad experience with, for example, Swing, because there is a lot of magic involved in this. It's like everything is discovered, but by the tool. But here is explicit, and you have full control of it. So that's the good kind of dependency injection. Yeah.
Yeah. So if I can comment on that. What I want to show is that dependency injection is just function application, which is something that should speak to every functional programmer. It's just a way of calling functions, calling other functions to build something, right? And the thing is, if we can make this operation have the ways to manipulate this, we get additional powers. If we can influence this construction, we can do more things with it, and we can say, oh, now do it slightly differently, and that's super helpful. Another way to see it is it's like type classes. Type classes are also doing that for you, but this one is programmable type classes. You can influence the ways things are being done.